Windows media player to play the video and then jump back into this one.
Let's skip over it.
Yeah. All right, thank you. Do you want to know
Thanks, everybody. This is the 5th research seminar series for the Deep South, Changing with Our Climate. Our apologies for getting a delay in getting started. We are, as always, pushing the technology to its limits and needed to be beaten back into shape. Thank you to everybody who's come in from both the different physical hubs across the country and people coming in from their individual PCs. This series has grown enormously over this year, and we now have up to 70 connections coming into Zoom, which is a great achievement and shows the broad interest these seminars have. Today's seminar features some of the work that is underway in our snow, ice and glacier project and work that has been picked up in a recent New Zealand Geographic article that you can see up there at the moment, called The Final Meltdown. So our presenters today are Andrew Mackintosh, who is a glaciologist at Victoria University, and Jono Conway, who is based at Bodeker Scientific. So halfway through, we will push the technology even further and switch from presenting in Wellington to presenting from Alexandra. So I hope that works. An advert for this evening. Deep South's research funded by Deep South, Belinda Story, is talking on the project on TV3 on some of our adaptation research, so please check that out. Now on to a bit of housekeeping for today. Please keep yourself muted throughout the seminar. During question time, our moderator will ensure that people are unmuted as needed. Please use the raise your hand to ask questions, which is on the chat panel in Zoom. If you're in a physical hub, we will look for physically raised hands, and your hub facilitator can raise the hand on Zoom so that we know which room you're connecting in from. Andrew and Jono will be about 20 minutes each, and so there'll be an opportunity for questions after they've both spoken. So I'll hand over to our first speaker, Andrew Mackintosh. Thanks, Andrew.
Just a minute, we're having some technical problems with people hearing us. Some can't, some can? Okay, so I'm told some people can hear us and some people can't, so we'll carry on. So some people can hear, so hopefully it's the people who can't hear maybe have issues at their ends, if other people can hear. Okay, great, we'll go. Yeah, thank you.
Kia ora and greetings, everybody. This title of the New Zealand Geographic article appeals to me as a child of the 80s. I will spare you the air guitar solo and singing that goes along with it. Anyway, we're very excited to see this published recently. So today I'm going to be talking about snow and ice, so glaciers as well as seasonal snow, and how they may be affected by a changing climate in the future. And to begin with, it's worth just pointing out why these elements of our system are important. They're important on various scales, both spatially and temporally. Locally, as glaciers change, they affect hazards. So you'll see some collapsing slopes in a minute, but also affect the tourist industry. But the tourist industry, of course, has national and global implications as well. Regionally, as sources of water, sort of melting snow and ice are critically important. And of course, that has a national implication because much of our power is generated from hydro in New Zealand. And of course, glaciers are also one of the largest contributors to sea level at the moment. They are, roughly speaking, adding about a third of the total sea level rise budget. So they are also globally important in terms of their contribution to sea level, although I must admit that the New Zealand glaciers themselves are not really adding very much to the oceans. It's more sort of glaciers in the northern hemisphere. And Jono and I are speaking today on behalf of a team, and in fact, one of the most rewarding and successful aspects of this project is the fact that it's brought together the leading snow and ice researchers from around the country for the first time. Before this Deep South project, we've never had a single program that has sort of brought us together. And this includes researchers at 3 universities, Victoria, Canterbury and Otago. I'm the PI along with Nicholas Cullen at Otago, and also Bodeker Scientific at Aqualink Research Limited in Christchurch. So it really is a nice connection between universities and also research institutes that have sort of more of a practical implication for understanding water resources. So most of the glaciers, as you probably know, in New Zealand are located in the South Island. In fact, most of the ice volume itself, the most massive area of ice, is located just within a few tens of kilometres of Araki Mount Cook in New Zealand. But we of course have glaciers that are spread throughout the Southern Alps, all the way from the bottom tip of Fiordland up to not too far sort of south of Cook Strait, small glaciers covering the entire range of the South Island. And in terms of their impacts on water resources, that's really dominated, the dominant effect is sort of in the Mackenzie Basin area on the eastern side of the Southern Alps. Glaciers, of course, also occur on the highest parts of Mount Ruapehu in the North Island. So there are a few small glaciers left up there. For those of you like myself who enjoy a bit of ski touring, you'll see them if you ski around up on the highest parts of Ruapehu. But seasonal snow is a persistent element in the mountain ranges of both islands, both north and south. So in terms of snowmelt, we're really talking about something that's of national significance. For glacier melt, most of the impact is in the South Island. And here you can see some quotes from various stakeholders who have an interest in snow and ice resources. And I'm sorry, the top one is cut out a little bit, so you can't see who it's from. But you can see that the idea is, in terms of importance, the main point I want to make here is that snow and ice is important to different groups and sort of regions for different reasons. So for some groups, it's about snow and its spatial distribution and understanding what its effects might be on water resources. So we're really talking about particularly the input of snowmelt to, say, buffering drought in dry conditions. If there's not a lot of precipitation falling from the sky, then some of it can be locked up in seasonal snow that's melting during the spring and into the early summer, and it's providing water resources during time when there's sort of not much around otherwise. But it's also important for flooding. So in particular, if you have a heavy rainfall event on snow cover, you can generate large floods through that sort of snow, rain on snow sort of event. And another reason that snow is important is for water quality. So particularly for snowmelt, it's providing pristine waters to our rivers, and if we didn't have that sort of pristine water trapped in storage in snowpack, it might affect our water quality. So the impacts from snow and ice are quite diverse, and it depends on where you are in the country and who you're speaking to. Not progressing now, I don't think.
Back to the problem again. Can we go back? The only thing I can suggest is to stop the share. Ah, there you go. It's the video that's stopping it, I think.
Yeah.
Let's see if it plays. So I can stop the share and find it on the desktop if you'd like me to.
Yeah, I think it's worth it.
Yeah.
You can pop back to the start of it. Okay, so this is a time-lapse video of Fox Glacier in the South Island. It was created by Brian Anderson. It's showing the retreat of Fox over the last few years. It starts in 2014. I'm speaking quickly because the first part is the really exciting bit where the terminus collapsed, and it basically made it impossible to carry out walk-on guiding at Fox Glacier. So it was the time when we had a shift to sort of helicopter guiding. Now this is sort of a view more up the glacier, and you can see We're up to about 2016 now, and there was actually a slight advance. Did anyone see it? Just a slight sort of bulging of the terminus. But into 2017 now, particularly one of the warmest summers on record, so the summer's about to begin. We're in October now. You can see the terminus is really sinking down, and in fact, we're retreating so much that we're changing from one terminus to another. So now the terminus was really up valley, right? So this is just to show you that glaciers really are changing, and even though the rest of my talk is mostly based on computer modelling, it's important to realise that we actually have observations of change as well, and the models are not without some sort of basis in reality as well on how glaciers are actually changing. So it looks like we're getting a loop of this, which is great. You can see the terminus now. There was a small advance in 2016, a slight bulging of the terminus. You can see the hillside collapsing the whole time during this video as well. The rate of hillside collapse, it speeds up when it rains, but it also depends on exactly where the ice is buttressing it, so it changes as the glacier retreats up valley. So this is a great teaching tool. It really can point out many of the effects that sort of relate changing glaciers to the sort of local impacts on a landscape and how that affects tourism, right? So for the future simulations that I'm about to show you for New Zealand glaciers, you have to remember that all of these sorts of impacts will occur, but on a completely different scale. Right. Brian Anderson has set up time-lapse cameras on a number of different glaciers in New Zealand now, and this is just one of them actually, and several of them are up on Vimeo, so it's worth having a look at them. The time lapses for Franz Josef are also really spectacular. You can blame Brian for the giant file that seems to have crashed the NEIL system.
Yeah, it does. Is that the next slide?
That is, yep, thanks.
Okay. Oh, that's working. Okay.
Right, so
No, it's not working, sorry, because we're not sharing. Not yet, no.
We good? Is that in?
No, put it in slideshow format.
Right. So you've probably realised by now that I'm focusing on glaciers, and Jono will talk about snow. In thinking about how... Are we good?
No, I was just trying to...
Yeah, that's right. If we're thinking about how glaciers affect river flows, here's a sort of an idealised graph that shows what we might expect in the future for glaciers. So here we have temperature that is warming over a certain period. So you can imagine this is today, and that might be 2100. Initially, we would expect a warming climate to create more water in glaciarized catchments because there'll be more melt, right? It's pretty clear. But at some point, glaciers will get small enough that their contribution to river flows will start to diminish. So there's this sort of concept of peak water in glaciology. For a certain while, we expect to see more water, and then we'll get less. It depends on where we are in the world, of course. So in the European Alps, for example, this recent study of Huss and Hock suggested that European glaciers have already passed their peak water. But if we go to places like the Himalayas, there's still some decades ahead until we reach peak water because the glaciers there are so large. For New Zealand, we actually don't really know quite where the peak water sort of sweet spot, if you like, sits for our glaciers. So now I'm going to show you some simulations of the future of New Zealand glaciers. This is focused really on the Aoraki Mount Cook domain. So again, within a few tens of kilometres of Mount Cook village, which you can see down here. But it includes glaciers that flow on both the eastern and western sides of the Southern Alps. And the large one in the centre here is Tasman, which wraps up a great deal of New Zealand's total ice volume. We had a master's student working on this a few years ago, mapping the distribution of ice thickness over Tasman. It's more than 600 metres in its central part today, right? So there's still a lot of ice left in the Southern Alps. And the fastest flowing and most iconic glaciers are Fox and Franz Josef flowing down the western side, and you just saw a time lapse for Fox. So this is a glacier simulation, so it's a computer model based on the physics of ice flow that includes the mass balance, so the snowfall and melt calculated with models that themselves are driven either by climate data sets like the NIWA VCSN data set, or a climate model, as you'll see for the future simulations. And those linked models together create simulated ice extent, and you can see here the model simulation for the present day, which is 2009. It looks pretty good, except for in places where we have large lakes forming at the terminus of glaciers. It's notoriously difficult to simulate the iceberg carving processes that cause those lakes to form. Sometimes the model does a better job or a worse job, and you'll see that what it does in the future. But nevertheless, at least for the simple glaciers in the Southern Alps, at this starting point, we seem to have a pretty good ice distribution, and this is based on a simulation that started in the late 19th century and sort of reached its current sort of, it's not an equilibrium position, but it's a transient position in 2009 in this snapshot. Now, under RCP 8.5, and there should be a gasp at this point, right? A gasp. There's very little ice left in this particular simulation. Now, of course, this is not reality. We don't know exactly what's going to happen, but it's an indication of what might happen to glaciers in the Southern Alps if we follow the RCP 8.5 scenario, which of course is sort of unmitigated climate change, results in about 4 degrees of warming, and the climate model forcing from this comes from Upper Sud. It's regional climate modelling that's downscaled from the CMIP5 models, choosing 6 models in particular. And if you look on this particular plot, you can see for some glaciers there are a few different lines. Each one of them represents a different climate model output. So, of course, the climate models all differ a little bit, so exactly how much ice you get depends on the exact climate model forcing that is used. But you can see anyway, there's not much ice left, and it's dominantly left on the highest peaks of the Southern Alps. However, under RCP 2.6, so here we have climate change mitigation, we have carbon capture, a reversal of our carbon trajectory, about a degree of warming in the Southern Alps. We end up with glaciers that are significantly smaller today. However, there's still parts of the landscape that would be iconic and identifiable, still a feature of the Southern Alps that might draw tourists to our country and so on, right? So there's still a significant part of our scenery under RCP 2.6. One of the great sources of uncertainty in thinking about what glaciers might do in the future is the effect of surface debris cover. So here you can see on the left a photo taken by Heather Purdy of Tasman Glacier covered in debris with a climate station sitting on the surface. And to the right you can see the simulations like the ones that I just showed you. The blue part this is actually an RCP 4.5 scenario at 2050, so it's a mid-century, it's a mid-level kind of climate change scenario. And where you can see the dark blue, that's the simulation of what glaciers will be doing under RCP 4.5 at 2050 if they're clean surfaced, there's no surface debris. But the other outline with the sort of lighter colour shows you the large areas of glacier ice that will be left behind if there is surface debris cover. We know there's surface debris today, so it's just trying to show you the sort of extreme effects of whether you include surface debris or not. And the trick is that there's actually many different ways to consider surface debris in terms of its physical equations and the effect on the surface energy balance. And from a physics point of view, we can do a reasonable job with that at the moment, but what we really don't know is how thick the debris is and how it's distributed over glaciers. So there's a lot to learn about the actual sort of, if you like, boundary conditions that are required in order to make these simulations work properly. And if we have new information about debris thickness, debris distribution, with our current setup, we can probably do a pretty good job of simulating what might happen to glaciers in the future. And it's important because if large areas of debris-covered ice are left behind, they might persist for decades to centuries and provide water to rivers from glaciers, even during drought conditions during the summer months. Remember, there's 600 metres of ice at Tasman Glacier. It takes a while to melt that all away. So whether that ice sticks around or not is going to be critical for water resources, particularly in the Waitaki Basin. And this is fine. I'm trying to be quick because I know we've run out of time a little bit because of the technical issues. But here you can see a graph that shows how glaciers are likely to change in the future. And this is our first preliminary work for all New Zealand glaciers, so it's not just based on that domain around Aoraki Mount Cook. And you can see ice volume on the y-axis and year on the x-axis. And the simple message here, and this really is a powerful message, is that what happens to glaciers depends on what we do in terms of mitigation. Very clear. Of course, there are some uncertainties related to things like debris cover, but ultimately it's our choices in terms of mitigation that are going to make the biggest difference in terms of the outcome for glaciers and the trajectory that they're likely to follow. This is true for New Zealand, but it's also true globally. So when you're thinking about what the contribution of mountain glaciers might be to sea level over the next century, the choices we make are the critical factor here. Right, I'm going to switch over to Jono now to talk about snow.
Okay, thank you for playing catch up there. So we're just going to pass over to Jono Conway at Bodeker Scientific and give him control of the screen. Jono, you're now in control.
Alrighty, I'm the boss. Maybe. Not yet. Oh, yeah, there we go. Hello, yes. So I thought I'd start off with this picture looking up the Dart River Valley towards the Barrier Range, here to Lake Wakatipu, and just look at some of this fresh snow. This is in January, looking at some of the fresh snow on the hills, as well as some of the areas of snow under Mount Earnslaw on the right there. So this is the seasonal snow that we're talking about here, and this water that's falling during the winter being stored in the snow and is being released later in spring and summer. So we can think of seasonal snow as a reservoir in which we put water during the winter and we get it back out into the river in the spring and summer. So it has the corresponding impact on the flows. So in terms of just looking at the contribution of snow to the annual flow of some rivers, apologies to the people in the North Island. Talk's going to focus mostly on the South Island, but we are looking at the North Island as well, so you're not forgotten. So this is some work done by Tim Kerr at Aqualink, and he looked at the contribution of snow melt to the annual average flow. So basically, how much of the water in the river came from snow, was snow at some point. And you can see the bluer colours there are rivers in which they have a large portion of snow melt. So you can see the standout one is the Waitaki there, in the lowest sort of middle South Island, but also the Clutha River, 10%. So these are major hydroelectric rivers with a significant amount of snow melt. And then if we zoom in a little bit, we can see other catchments in the Southern Alps, the Rakaia, here to the Rangitata and the headwaters of the Rakaia, but also these smaller catchments that I've circled here in the south, the Waikaia, the Nevis, the Fraser, headwaters of the Manuherikia, and the Apua Dam in central Canterbury. And they're all areas that have irrigation dams on them. So they are, so snow is significant both for the hydroelectric but also for the irrigation storage. So snow is variable, seasonal snow. That's, I guess, one of the messages from today is it's variable from place to place in terms of its importance, but also from year to year. And this figure here shows it's from Meridian Energy, from some of the modelling work they do, estimating the amount of water stored in the Waitaki, apologies for spelling there, in the Waitaki catchment as a whole, from late autumn through the winter and summer. And so you can see the green area here is the interannual variability in how much snow can be in the snow in that catchment. And that's quite large when you compare it to the mean line there. So it's sort of plus or minus 50%. So it's really variable. you can get a quite variable amount of snow. And so just thinking about what we expect with climate change. So this is an example from some work done by Andy Jobst at University of Otago, and he looked at the Clutha catchment, and the blue shading there is a similar plot to the Meridian one, again from late autumn through the winter and on to summer, and you can see a peak storage there around September, October, early spring. And so the grey and the orange boxes are future scenarios for mid-century, so 2050, showing the expected decrease in storage, earlier snow melt. And that's due primarily to more snow, more precipitation falling as rain rather than snow. And the earlier melt is due to less fresh snow in spring, which means that the snow is reflecting less of the sunlight, but also due to the air being warmer and that melting. And so that has a corresponding effect on the river flows. So this is the same example, same scenario, same colours, but now looking at river flows in the Clutha at basically its outlet to the sea at Clutha. So you can see in the winter there, through June through September, in the future, the projection is that there will be higher river flows in the winter, and then a little less clear, certainly at mid-century, but lower flows during the summer. So that's the expected pattern. Yeah. So I guess the question is, what are we doing? What is our team doing as far as seasonal snow in the Deep South Challenge? And one of our main tasks is to implement a new snow model into the New Zealand water model, which is the TopNet hydrological model. And why we need to do this is, well, when we look at the energy that's used to melt snow in New Zealand, and I've just got this example here, a figure from work we've done on Brewster Glacier, we see that solar radiation, or that the energy from the sun, this yellow bar, is by far the king when it comes to melt. Other components, the sensible and latent heat, which is related to the temperature of the air, are important for large melt events. And you'll see some small losses there at the bottom, the green and the orange. So there's some things we're trying to heat up. We're trying to heat up the cold snowpack, and we're losing some energy that radiates from the surface of the snow. But by far the solar radiation is king. But in the current snow model that we have in TopNet, it doesn't explicitly include solar radiation. The melt it depends on temperature and precipitation. And so this is important, and when we thinking about climate change scenarios, because we may be overestimating the response to increased air temperature if our melt is only dependent on air temperature. So the new model will have a better physical basis for melt, for the projections. So what we're doing is we're implementing a model that separates melt due to solar radiation and the melt due to energy from the warm air. And this is important because we can now get more melt on north-facing slopes and less on south. And if we this picture here is from the Pisa Range, central Otago, looking at a north-facing slope devoid of snow, and some low-lying and south-facing slopes with more snow on them. Now, partly this is related to where snow is deposited, but it also depends on the amount of energy that's coming into that slope. And these thicker snowpacks on the south-facing or non-north-facing slopes, they release their water later. So that's why it's important to account for. And we can also, with the new model, we'll account for seasonal differences in melt energy, and also explicitly accounts for how much light the snow reflects, which is more after new snow. And that's important because we can get the feedbacks between snowfall and melt. So where we have fresh snow, it is reflecting more sunlight and therefore creating less melt than if we didn't have that snowfall. And that accounts for a lot of the sensitivity to air temperature, is actually the relationship, actually whether or not we get snow replenishing the highly reflective surface. So I've tested the new model on some data sets that we collected up on the Brewster Glacier. So this is part of my PhD, was to run a weather station for 2 years on the glacier, and that was both challenging and rewarding, dealing with 3-4 meters of snowfall and a lot of ice melt. But yeah, it's a big motivation for the modelling work I do to be able to go and actually be in the real world. So, and this data is crucial for like Andrew was saying, for testing our models on what's actually going on. So if we just look at the figure there, we'll see the snow depth through the winter here, from May through into early summer. You see it accumulating after a number of different snowfalls, one big snowfall in particular this year in mid-July. And you'll see that our model, which is the orange one, is tracking fairly well with the red, which is the observed snow height. So that's giving us confidence that we're doing well, and we're doing well against a more sophisticated model, which is the green one, which is capturing all the different components of melt based on those energy fluxes. So we're doing good. So the other advance that I guess we have, that we're able to have now over previous projections that were done, which were about 10 years old now, done by Jordi Hendricks and Martin Clark, is the ability to use satellite data sets. So we're looking here at the Clutha catchments now, from the lakes Wanaka, Mokatipu and Hawea, down through Central Otago to the outlet at the bottom there. And the scale is the average number of days with snow on the ground. So basically the snow cover duration, how long is the snow sitting. So this is a 17-year record, and it's from the MODIS satellite. And you'll see up on the top left there, some areas with close to 360-day snowfall. So that's the permanent areas of snow. But you'll also see out and through, as we come further east, areas with close to half the year with snowfall, or with snow covering the ground. So it's significant, yeah. And now if we look at at the model, this is the same area, but this is now the model simulation at 250 meter grid. You'll see two things there. One is it's much bluer or purpler, and the other it's more finely resolved. If we just flip between those two, you'll see in the headwaters it's much more finely resolved. But on the main, what we see when we look at this is there's much less snow out east. So I'll deal with each of them in turn. For the first one, the snow out in the central areas, is basically not enough snowfall happening. It's not melting too quick. It's just not falling in the model. So this is related to the climate data that we're using, and it's basically too warm. The climate data, we have to get biases. We have to turn temperature down by about 5 degrees to get enough snow to accumulate in these areas to match with the satellite observations. And we've tested this with 3 different data sets from different sources, and we get the same sort of story. And there's 2 things that this tells me, and one's that snow is really sensitive to temperature, and so in a warmer world we are going to see larger changes. So that's good. But B, we're really dependent on the quality of the data that we can use. Both the reanalyses that we're using here to to tune and reality check our model, but also in terms of the projections. And so I think this is an area for future work. And I think scraping data essentially from other sources in these high elevation areas and using smart tools, machine learning, and high resolution weather models, reanalysis, I think is an area which will greatly improve our ability and our confidence in the models and the projections. So for now, we can work around them. We can tune the model to the satellite record, but ultimately with better data sets to support it, we'll be in a much better place to make predictions and have confidence in it. So just to wrap up, so some progress as far as the project's going. So we're enhancing snow and glacier models. We're working on implementing these into the New Zealand water model, and so from that we'll be able to have projections of how much snow is going to change with the latest scenarios. So this will be a New Zealand-wide assessment, and then they will also feed directly into the impacts on water resources. Like I said, the quality of those will depend on what inputs we have, both in the future and historically. And one big uncertainty that we have is the spatial pattern of precipitation and snow in these high mountain areas. Because if we're going to get larger amounts of precipitation, then that may bring additional snow that's going to offset the amount. So we could have areas in which more precipitation equals more snow rather than less snow. So I guess the consensus from the group is major retreat, like Andrew was showing, but again, that magnitude depends on what we do and the choices we make for the future scenarios. For the glaciers, the surface debris, that big model physics question to resolve. As far as seasonal snow, we're talking about less, but I think it's important to recognise that variability that we have from year to year will mean we'll always have some seasons when there's a good amount of snowfall and indeed positive mass balance on the glaciers, years in which it accumulates more snow than melts. So there'll still be the variability there. We're not going to lose our snow. We're just going to have less, and that's going to likely increase the river flows in winter and decrease them in summer. And that's going to present maybe some opportunities for hydropower if they can use that extra water that's going to be flowing in winter during the time of peak demand. And maybe some challenges for irrigators as the timing of that snow melt moves earlier in the season when it's less useful for growing crops. And that's a wrap.
Okay, so thank you very much to both of our speakers, to Andrew Mackintosh and Jono Conway. I am just going to stop sharing so we can see who's with us, and we've got about 15 minutes for questions. You can either, as Mike said at the beginning, if you're just on a Zoom connection somewhere, you can raise your hand through Zoom, or you can simply try raising your hand physically if we can see you and you're in a hub, or if you're here in Wellington. We will try and go between people as questions come up, and if you could please just introduce yourself, and if the question's particularly directed to Andrew or Jono, then let us know. So, would you like to come up here? Yeah, we do have a question here from Niwa Wellington. Yeah.
Can you show
Is it on?
Can you show I forgot exactly what.
becoming more technical.
Maybe come up to the front.
Oh.
I can speak louder. Can you show the few slides at the beginning? It shows the distribution of the ice, snow ice thickness. That man.
I'm not sure how to show it, so I can see it on here.
Just do you want to go back to a slide?
Just go back to slides.
Okay.
Okay, that's fine.
The simulation of the thickness of snow.
Is that the one you mean?
Yes.
Well, hang on.
The legend shows the unit as meter.
Yeah.
So is the thickness between about 500 meter? So maybe I'm wrong.
Yes. I mean, that's about the maximum thickness, but on average, it's much less than that.
500 meter thickness.
Yeah, so in the central part of Tasman Glacier here, you can see...
This is quite a surprise to me, is 500 meter. It's more than the highest mountains of Wellington.
It is, yeah. Thanks for
But do you have any observations to show that?
Sorry?
Do you have any observation to show that?
Of course. I mean, we could always have more.
Because this is actually I don't believe, because I checked some of the publications before it shows observations of the thickness is at most of stations about 50 meters is at most. So it's quite a surprise to me.
Well, I guess you should probably acknowledge that we're the experts, and it's based on observations rather than, But that said, there aren't that many observations. So our ice thickness distribution here comes from two sources. One is an inversion that's based on the.
You mean the total accumulation is 500 meters?
The other.
Okay.
Yeah.
A lot of accumulation is the thickness.
Thickness of
Thickness.
glaciers. Yeah.
Okay, so in a valley, for example, in a valley that is slow accumulated there. So for a long time period, maybe more than 1,000 years, so it's like the thickness could be about 500 meters.
Yeah, I mean, you could grow ice that's 500 meters thick in a few centuries. You don't need thousands of years. You can see that just by using the models growing from ice-free conditions. But there are seismic observations, and we've been recently doing gravity observations that confirm. There is some uncertainty there, but the uncertainty would be in the order of 10%. So we're either 600 or 400 or something in the thickest parts. But there's no doubt that there's half a kilometre of ice, roughly speaking, in the middle of Tasman Glacier. Yeah.
Another question, maybe a comment about the snow simulation. So you use the snow model with the climate model projection to drive the model. And the model actually is as the EWA question on the snow model. The snow model is as the EWA question.
No, I mean this is a glacier model which includes the snow components. It's mostly Brian Anderson's work, who works with me up at Victoria University. Yeah.
So this is only a conceptual model.
Well, it's not really a conceptual model. It's a
simple one. It just considers the precipitation and simple mating.
I mean all models. All models have got uncertainties, but it's a physical model, not a conceptual model that includes the physical processes of ice flow. I mean, some of the largest uncertainties here, like Jono was saying, for the snow models are based more around the climate inputs rather than the way that ice is redistributed. I think we all have to acknowledge that we don't have enough in the way of observations of precipitation and temperature, in fact, over the rugged mountains of the South Island.
Thanks, Andrew. One of the interesting things about this research, of course, is the downstream implications.
Yeah.
If we have rapid ice loss, and I'm not sure if you guys can necessarily answer this, will we be able to gain the full benefits of that, or in terms of hydroelectricity generation, or are we actually likely to be in the situation where the loss is sufficiently rapid that that water will be spilt down the Waitaki Valley?
Yeah, I mean that's a really good question, and I don't think I'm in a position to answer it properly. But I think we need to know the answer to that in order to work out exactly what the impacts are going to be. I don't know if Jono wants to make a comment about that one.
No, I'd agree with Andrew. We're not really in a position to comment. I guess with a change, if we lose the glaciers rapidly, we're getting into a situation where we're exposed to more variability from year to year. Glaciers are, sort of slow and steady. If it's a hot summer, you're getting melt from the glacier. Seasonal snow comes in the winter. It's a light winter. It's all gone by December, and then it's whatever rain falls and whatever base flow is coming out. So I think switching between a regime which has some glacier buffering in summer there to one that's entirely just rain and snow is more variable. You're getting to a more variable place. So in terms of can you capture that and cope with the peak flows that are coming down through your system, and that's, I guess, where we need to look more at the hydrology and work more with the generators on that.
Mr. David in the back first. Yes, thanks.
Yeah, thanks, and thanks very much to both of you. That's been a fascinating talk. But just sort of following on from that question, I guess the question I had was just where the meridians, the generators, how are they interacting with you on this work? Are they showing interest in it and getting involved with you?
So I think we've had some really productive conversations with power generators. So the way our engagement works within our project is that each of us has people assigned that we talk to. So I can't sort of answer that question directly because Heather Purdy, for example, and Tim Kerr and others have been talking with power generators. But they're certainly involved. I think if we're funded in the next phase of the Deep South, I think it would be great to have a bit of a stock take and sort of recalibration of what's required from South Island power generators. Yeah, but so it's a good question. Thanks, David.
Okay, thank you. We're just going to move to Victoria University where somebody wants to ask a question now. Maybe one of your students.
Well, not actually one of his students, but sorry. A little less relevant, I admit, but I was wondering what you could tell me about the modelled or observed in any kinds of records changes in South Island glaciation over the past few centuries, or if there's any papers that I could learn about that from relating to my research?
Sure. So I guess we know quite a lot more about how glaciers have changed over the last century than what we do for the future. And there are a number of publications about that. I mean, best way is probably just to catch me independently to get a sort of reference list. But the observations of New Zealand glaciers go back quite a long way for the, relative to where we're located. So more than 100 years. We're lucky that some of the early surveyors like Broderick and so on actually created beautiful maps of the glaciers in the South Island, or at least the main ones, more than a century ago. And in the model simulation that I showed that's been carried out by Brian, he uses those 19th century maps to kind of start the simulations to get a steady state ice geometry that looks quite reasonable, and then imposes about sort of 0.6 degree of warming during the 20th century to retreat the glaciers as observed. And for Franz Josef, there's nearly a century of length observations that are quite well matched in that model study. And Brian Anderson and myself and Drew Laurie from NIWA and others just recently wrote a paper about the sort of unusual advance of New Zealand glaciers, published in Nature Communications in 2017, that explains why that sort of blip of re-advance occurred in a climate that's sort of changing. Seems a bit surprising, but with changing atmospheric circulation and sea surface temperatures, it's relatively easy to explain based on variability in climate. Having said that, in a future climate which might be up to 4 degrees warmer, there's no way that such variability will have enough effect to overwhelm the retreat pattern that we're simulating. So I've sort of gone a bit broader than the question. But yeah.
Okay, thanks, Andrew. We've got another question here at Wellington.
Hello, thanks. If I remember correctly, New Zealand glaciers have in the past at least reacted differently to climate forcing than glaciers elsewhere. I think there's a suggestion that they are more precipitation driven than temperature driven, at least compared to other areas. Is that going to be a problem for the modeling, and how would the future evolution compare to other parts of the world?
So the sort of temperature versus precipitation question for glaciers is something that interests me a lot, and we've got a track record of publishing many papers about this, and there's a debate, although I don't think there's much of a debate anymore. It's clearly temperature that's driving the glaciers for the most part, although there's a relationship with the precipitation. So Jono mentioned, for example, albedo effects. So if it's cold enough for precipitation to fall as snow rather than rain, then glaciers get a lot brighter and reflect incoming solar radiation back to space. So it's the temperature that's sort of modulating the precipitation signal to some degree. And actually global studies have shown that high precipitation glaciers are even more sensitive to temperature change than drier sort of area glaciers. That's not to say that in a climate that's variable like what we have in New Zealand, we wouldn't expect to see glaciers advancing and retreating a little bit due to mostly to atmospheric circulation and ocean variability. That because the glaciers are so sensitive allows them to sort of flick around a little bit in a climate that should otherwise be causing glaciers to retreat. So if you compare, for example, what's happened to glaciers in the European Alps to New Zealand, we see more variability, but we think that's got to do with the climate being more variable than the glaciers being more sensitive to precipitation, if that makes sense.
Fascinating. We've got time for one more question, and I think it's coming from the back row. If you could just introduce yourself, please.
Yeah, hi, I'm Craig Stewart. I'm an oceanographer here at NIWA. I'm just interested, that model prediction of the reduction in the glacier area was pretty shocking. What would you say the main uncertainties in that prediction are? I was particularly interested in the comments later in the talk about maybe it was a degree day approach rather than a full, radiation energy balance at the surface.
Yeah.
Is that something you expect might change your sensitivity to temperature, or is it the uncertainty in that atmospheric sort of forcing?
Are you talking about RCP 8.5 in particular? So.
Yes, I guess I was talking about the plot that you see there, but maybe more in general, what you see as the big uncertainties and.
So we have, and this is true for our groups, in Otago as well as Wellington. We've got a track record of using full surface energy balance models to calculate mass balance over glaciers. But the real question is, can you use a simpler model like a degree day model or a modified one like the one Jono was talking about, to capture the majority of the glacier response? If you can, then obviously there are advantages because you can apply it much more quickly within a computing framework and do it for whole domains as large as New Zealand rather than just sort of smaller scale domains. So we've spent a lot of time asking ourselves those questions, and I think that you can get a pretty good result using a sort of modified degree day model that includes solar radiation. So that's sort of part of your answer to your question. In thinking about RCP 8.5 and what might happen to glaciers and what the greatest uncertainty is there, for these very warm climate change scenarios, the debris cover ceases to be such an important issue because basically just all the ice is lost. And then the greatest uncertainty is probably related more to the range of climate models rather than sort of anything else. So it really depends on what extreme you look at within the ensemble of CMIP5 models, for example. And then after that, it would come down to, particularly on a regional scale, how well we understand present-day distributions of temperature and precipitation and so on, which is not that well in some areas. All of these things introduce uncertainties, but the dominant signal of climate warming overwhelms any of these other uncertainties, and I think gives us considerable confidence in the fact that we're going to lose most of the glaciers under 4 degrees of warming like we expect for RCP 8.5.
Thank you.
You're welcome.
Okay, thank you very much to Andrew Mackintosh and Jono Conway. That was a fascinating seminar, and we're really looking forward to more outputs from the research, which is of great relevance to many people in New Zealand. So thank you for that. I just also wanted to acknowledge that this is the last Deep South Challenge seminar of the year. It's also the 10th one that we've hosted, and that was probably the most challenging. We've never had that many technical hiccups, so we got through it. But I want to acknowledge Alex Keeble for all the work that she puts in behind the scenes, Carolyn O'Brien, and also the people at the organisations that do support us through setting all of these things up. There's quite a lot of work that goes on behind the scenes. So thank you to our speakers, and thank you to the team that make these seminars successful. And we'll see you in 2019. Yeah, thanks.